Ready? If you dove into the ocean off the coast of Sicily, you'd suddenly be surrounded by over 900 of these mysterious balls. Like these. They hook these up on a string, wind them up into an even bigger ball, and then drop them into the ocean, where they unroll to nearly twice the height of the Empire State Building, again and again and again, creating this massive forest of floating spheres. And on the surface, hidden inside an abandoned winery, a computer watches them and waits. And in 2023, they saw something way smaller than an electron, tore through this forest at nearly the speed of light, setting off a signal nearly 30 times more powerful than anything we'd ever seen like it before. Which means that something huge must have happened way out there in space. So all of these telescopes all around the world swing in that direction to see what it might be. And they find nothing. Now, scientists are searching for answers, and this crazy experiment is getting bigger. But it's not alone. Down at the bottom of the world, buried deep in Antarctic ice, are over 5,000 more of these mysterious balls. This is Ice Cube, and this is KM3net. And together, they're part of a massive global effort to give us a brand new way to find and look inside the biggest, most extreme cosmic events in our universe. But to do it, they need to catch the most elusive particle in all of physics. And we're gonna show you how. This episode was made possible by AT&T, the official connectivity partner of Huge If True. Imagine that you and I get into a spaceship and we fly to the next closest star. It's nearly 40 trillion kilometers away, a distance that could fit nearly 29 million of our sun, which means that we're flying for 75,000 years. And that's just about the average distance for all the stars in our galaxy. There's just a lot of space in space. If instead, we shrink down to the size of one of the tiniest fundamental particles in physics, the space between the stars would be like the distance between the nucleus of atoms to us now. That means that we could zoom right through the atoms of solid rock as easily as flying between the stars in space. That is what it's like to be a neutrino. It's another fundamental particle, like electrons, but way smaller. If you scaled this particle up, even just a millimeter in size, a human being would be like the size of an entire galaxy. It's really hard to understand just how close to nothing these particles actually are. Their nickname is the ghost particle because they pass through basically everything. Stars, planets, walls, even you. Every single second, 100 trillion neutrinos pass through your body. Hold up your thumb right now. That's what's happening right there. But this fly-through-walls superpower is what makes neutrinos so awesome as a way to study what's really happening out there in our universe. Because everything else that we've used so far has a big problem. When we want to understand what's happening way out there, we can only use what reaches us. And up until this point, there have been 3 options. Most of the time, we use option 1, light. Not just visible light, but everything made up of photons, radio waves, infrared, gamma rays, but other things reach us too, like option 2, these really high-energy charged particles called cosmic rays. Scientists study these to learn about the chemistry of deep space. And option 3, ripples in space-time called gravitational waves. But while these methods have taught us so much, the big problem is this one gets blocked, reflected, and warped. This one gets tossed around by magnetic fields in space, and this one can only tell us when something massive happens, not what it did or what it's made of. Meaning there are things that we might never discover because the evidence took a wrong turn on the way to Earth. That is why neutrinos are special. They're a new 4th option to study what's out there. Their size means they're incredibly unlikely to get blocked by anything in their path. And they have no charge, so they don't get warped by electric or magnetic fields, which means that they travel straight to us at almost the speed of light. If you can catch neutrinos, you can trace back exactly where they came from, and even see inside whatever made them. A good analogy would be a doctor giving you an exam. Visible light can show them some things, but if they wanted to see your bones,
you can use X-rays, right? And the reason X-rays are useful is because they can interact with muscle and tissue and skin less than ordinary kinds of light do.
So catching neutrinos is like developing X-ray vision for our universe. So for example, around every 10 seconds, somewhere in the universe, a star collapses in a supernova, releasing a massive burst of energy, blasting particles out into the universe at up to 40,000 kilometers per second. We think these explosions are the primary sources of elements like silicon and oxygen and iron. And those elements make up the universe and planets and us. The iron in your blood can be traced back to a supernova, which is why these events are called cosmic engines. Scientists think that cosmic rays come from here, but they can't be positive because we can't trace them. And light can show us the aftermath of a supernova, but light takes forever to get out past all this dense matter at the center. So,
if you want to know what's going on inside the core of a supernova, neutrinos are your messenger.
But wait, if the whole point is that neutrinos are so special to study because they can go through anything, how do you catch one?
The problem is that neutrinos interact so weakly that if it's great for them to pass through everything, well, they can also pass through our own detectors.
How do you study something that never interacts with you at all? You build a very, very big and very crazy machine. So right now, I'm at the lab in Caserta, Italy, where they're putting together the detectors that make up this giant underwater experiment. When this experiment is finished, it'll take up a cubic kilometer in the Mediterranean Sea. That's where its name comes from, Cubic Kilometer Neutrino Telescope. The entire project is technically 2 telescopes, and we're focusing on this bigger one over here. Each of these spheres is called a dome. And inside each dome is a huge amount of delicate tech that has to survive in the deep sea. And they piece each one together, here, by hand, one hemisphere at a time. You start with one glass half, and this aluminum piece right here, that you glue in place with this special gel.
Pay attention to the air bubbles.
Okay.
It's done.
It's done!
Well done. And sign it, by the way. Yeah. Go on.
Thank you.
You're welcome.
That's the huge dome. Now the huge dome needs a brain, a mini computer that tells it what to do, and 31 of these. These are its eyes, the photomultipliers, which you fit very carefully into this 3D printed frame. He's checking my work.
Yeah, I did a good job, all things considered, for the first time.
The most important thing here is that these photomultipliers are incredibly sensitive to light. Each one is sensitive enough to detect a single photon. That's insane. That's like standing in the middle of a hurricane and hearing a single drop on a single leaf. But wait, this is a neutrino telescope. Why are we trying to detect light?
So we actually cannot see neutrino.
Wait, what?
We don't have the technology to do that, even though there are hundreds of them in every cubic centimeter of space today.
So instead, they found a very clever way to detect what happens in the unlikely times when a neutrino actually does just happen to crash into something. From the little neutrino's perspective, what happens is it's born in some massive cosmic event like a supernova or a supermassive black hole with jets of plasma, but it escapes. And for the next billion years, it goes in a straight line.
Not that they're sentient or something, but if they were, it would be a dull billion years.
And then, one day,
And then they come up to this little pale blue dot, Earth, and they don't really care that it's there. You know, they've traveled through a lot of stuff.
But not this time. This neutrino just happens to fly right through the Earth. And then, just by chance, it accidentally runs headfirst into some poor proton. And that proton just happens to be inside a water molecule right here off Sicily. Or inside the ice right here in Antarctica, which I know sounds incredibly unlikely, but remember, 100 trillion of them through your body every single second. So statistically, some of them will bump into something. And when that happens... Wait, slow that down. The neutrino hits the proton, changing it into a different, heavier particle, which flies through the water faster than light. This is part of the reason why KM3net sits 3,500 meters underwater. And nothing can go faster than the speed of light in vacuum. But light slows down a lot in water. So there are actually particles that can go faster than the speed of light in water. And when they do, they create waves of light, making this cone shape behind them. Is it sort of like a sonic boom? Something is moving faster than sound, and so there's like a wave around it in a cone?
It is exactly like a sonic boom.
In this case, instead of going faster than the speed of sound and making a boom, they go faster than the speed of light in water and make a flash of blue light. That is what these sensors can see. If you were down there in the water with your eyes wide open, this is visible light. But most of the flash is so faint and so fast that your eyes probably couldn't see it. But that's what these sensors were built for.
That light is picked up by hundreds or maybe thousands of these optical sensors.
Every detector has to be exactly the same. Every photomultiplier has to be in perfect sync. When this experiment is fully built, there are going to be over 4,000 of these at the bottom of the Mediterranean Sea.
It takes about a month to build and test 18 DOMs, which is just one single string. And then you spool that string up into
What they call LOMs, which are these giant balls. This is what they're going to drop into the ocean.
On the top is a buoy to hold them up, and on the bottom is an anchor with a base module.
And then from the bottom of the base module, there are these big orange cables that connect all the way to the shore.
To that abandoned winery turned science lab, where
They're gathered together a computer, and next thing you know, some scientists are looking at this and saying, hey, I think we just saw a neutrino.
But it's really hard to make sure that this computer sees just this special blue light and not anything else. Because while there's less light down there, it's not zero. They have to ignore
Lots and lots of photons created by all kinds of things like bioluminescent microorganisms.
and all kinds of other particles raining down on this machine from above. In order to weed those out, these machines mostly look at particles small enough to pass through the Earth. So,
When you're thinking about this experiment, don't think about it like hundreds of detectors on strings sticking up out of the ocean and looking up above it. Think about it instead as the back of a giant telescope where the lens is the entire Earth.
KM3net won't be completely done for a few more years. It's operational right now, but it's not at its full capacity. But down in Antarctica is its sister, Ice Cube. That one's been operational for over a decade now. Instead of water, they use ice, which on its own is a massive engineering feat. And because each experiment is mostly focusing on neutrinos coming through the Earth, this is what KM3net sees. And this is what Ice Cube sees. They complete each other. Just take a second to think about how incredible this is. Humans are amazing, but what's amazing isn't just the infrastructure, it's also what they found with it. In 2017, a high-energy neutrino tore through Antarctic ice, setting off Ice Cube and telling scientists around the world to swing their telescopes in that direction. And they found a flaring active galaxy, a blazar over 4 billion light years away, that we'd seen before with visible light and gamma rays, but it wasn't until we saw the neutrino that we could confirm this is a cosmic engine, the source of heavy metals that make up everything, including us, and a source of cosmic rays. This moment marked the beginning of a whole new era in astronomy, one where we could use all 4 options, photons, cosmic rays, gravitational waves, and neutrinos, to see things in an entirely new way. And it took such a huge effort. Just look at this. There are nearly 1,000 scientists on this paper. This was a huge deal, and they just kept going. In 2022, Ice Cube identified an active galaxy nearly 50 million light years away. You can actually see it from the ground with a normal telescope. But its core was completely hidden by gas and dust. Light couldn't escape, so we couldn't see inside. But neutrinos could, and did. So we got the first ever look inside a cosmic engine that light could never show us.
This is one of the most exciting things to happen in modern astronomy. It's really a watershed moment, not just for neutrino astronomy, but for astrophysics in general.
And in 2023, when that most powerful signal ever came through KM3net, the one that we still don't know where it came from, it showed us that there is so much more to discover with neutrinos.
It's just, it opens a whole new kind of eye onto the universe. This is a truly, one of a kind of event in human experience so far.
We've created a new way to see inside our universe. And what I love most about this story isn't just what we could discover with neutrinos. It's also what the effort says about us as humans.
I was a factory worker before.
You're building this incredible thing that is gonna move forward our understanding of the universe.
Yeah, I'm pretty proud of that.
It's awesome.
Because what are the machines that we build, if not extensions of ourselves, to be our brain and our eyes and our ears, and take us places we could never go, and show us things we could never see? Huge if true. If you like this and you want more optimistic science and tech stories in your life, subscribe to support our show. And remember, this episode was made possible by AT&T, the official connectivity partner of Huge If True.